So let's look at some examples of how we can use our new washer method to find some actual volumes, right? The volumes generated by rotating some curves. So first, just for a reminder, right? Remember that the washer method says if we have two curves, two graphs, one on top of the other, and we revolve the region between them around, for now, the x-axis, then the volume generated by that revolution is pi times the integral from a to b of f of x squared minus g of x squared dx. And we do have the requirement here that f of x has to be the function on top, if you will, right? It has to be the greater of the two functions. So what am I asking for here? I'm trying to find the area between, the volume generated by revolving the region, gets a little long-winded, between the cosine of x and the sine of x between 0 and pi over 2. All right, so 0 is here. So we've got this section. And where's this going to end? It's going to end at pi over 2. Remember, cosine of pi over 2 is 0. So that's going to be this spot here where it crosses the x-axis again. So we have these two regions. We're going to get, I don't know, some very odd looking solid when we do this. So we do have this concern, right? The two graphs cross each other, right? And they cross each other here in the middle, right, at the point where the cosine of x equals the sine of x. And hopefully, you know, just by looking what the solution to this equation is, it's x equals pi over 4 plus k pi. But the only one we care about is this one right here between 0 and pi over 2. So this crossing point here is going to be at pi over 4. Right, so what I'm going to have to do is I'm going to have to do this as two integrals. Right, first I'll do the integral from 0 to pi over 4. Let me write it. Right, the volume is going to be the integral from 0 to pi over 4 of cosine squared x minus sine squared x dx. Don't forget the pi out in front. That's not enough room. Sorry, let me write this again. I'm gonna need more room for that to have the second integral there. So let me clear some space here. And I'll write it again. The volume is pi times the integral from 0 to pi over 4 of cosine squared x minus sine squared x dx plus pi times the integral from pi over 4 to pi over 2. And now we have to do it the other way around, right? Because in that right-hand section, the sine function is on top. So it'll be sine squared x minus cosine squared x dx. Okay, so how are we going to do these integrals? Well, this is one of those. You could do integral cosine squared minus integral sine squared and use some double angle identities in there somewhere. But look, it's easier, I think, and again, highlights the importance of knowing your basic trig identities. Cosine squared minus sine squared is cosine 2x. So I'm just going to make this pi times the integral 0 to pi over 4 cosine 2x dx. Now, look what I'm going to do over here. I've got sine squared minus cosine squared. That's backwards. Right? But if I factor a -1 out of that, this becomes negative pi integral pi over 4 to pi over 2. And now on the inside is cosine squared minus sine squared, which is also cosine 2x dx. Now be careful. You might be tempted to try to combine these together. You can't because the limits of integration are different. Right? One is 0 to pi over 4. The other is pi over 4 to pi over 2. So we really do need to continue doing these separately. The one thing I will do, just to make life a little easier, is factor this pi out in front. All right, so now this first one, this is 1/2 sine 2x from 0 to pi over 4 minus the same antiderivative, 1/2 sine 2x from pi over 4 to pi over 2. All right, so let's put our numbers in here. This is 1/2 sine 2 times pi over 4, so that's pi over 2, minus, I really should have factored that 1/2 out, shouldn't I? But I've already started, so we'll just keep going. 1/2 sine of 0 minus 1/2 sine of 0 minus 1/2, oh, well, not sine of 0, what am I saying? Sine of pi, right? 2 times pi over 2 minus 1/2 sine 2 times pi over 4, which is pi over 2. Make sure I got all my parentheses right in there. I think I did. Good. Okay, so this is pi times 1/2 times 1 minus 1/2 times 0 minus sine of pi is also 0, so that's 1/2 times 0 again, minus 1/2 times sine of pi over 2, which is 1. All right, so what is this? We should be able to get to the final result now, right? This is 1/2 minus 0 plus 1/2. Hey, 1/2 plus 1/2. That's just pi. Right, there you go. So that's my volume. Pi. We don't usually concern ourselves too much with units, but obviously it would be cubic, right? So pi cubic units. So here I have another similar question, but with a very common twist to the questions that we've seen so far. I want to rotate this about the y-axis rather than the x-axis. But just like all the other things we've seen, right, that just means switching the variables. So the volume for rotation around the x-axis is the integral from a to b of f of x squared minus g of x squared dx. Well, the volume around the y-axis is going to be the integral from a to, I'm going to run out of room here. Let me write it on top. Volume equals the integral from a to b of f of y squared minus g of y squared dy. And of course, the a and b down here are x values. The a and b up here are y values. So since we're rotating around the y-axis, I need to take both of these functions and solve them for y. So I mean, this one, solve them for x. This one, well, this is y equals x, x equals y. Here, so we have g of y equals y, not very interesting. Okay, over here we have y equals x squared, which means x equals the square root of y. So let's not use g, let's use a different letter. H of y, and over here k of y equals the square root of y. And we weren't given boundaries. Okay, that's okay. We'll have to solve for them. So come over here. Take a look at the picture. Right, I've graphed these two things here. This is the region that we're talking about rotating. So when we do this, if you kind of visualize in your head, we're going to get something like a cup. It's going to be rounded at the bottom, but it's going to have, because it comes to a point here, it's going to have something like a cone shaved out of the center of it. All right, so let's be really clear about which function is which here. This is the square root of y, and this one is y. So the square root of y function is, in a sense, the one that's on top is the one that has the greater values. So that's the one that's going to go first when we put these into the formula, right? And where do these two curves cross each other? Well, they cross each other where x equals x squared. You can do this with the y versions of the function. You're going to get the same answer either way. So this gives me x squared minus x equals 0, and you factor this, x times x minus 1, and we get really kind of the obvious results, right? I think that we're the x and y. Now these are x values, right? Now that I've said that, these are x values. What are the corresponding y values? Well, y equals f of 0 is 0, and y equals f of 1 is 1. So in this case, they happen to be the same, right? I'm going to integrate from 0 to 1. So let's go ahead and do this, right? I'm going to integrate from 0 to 1. And again, just which one is bigger? When we're rotating around the x-axis, we're looking at which graph has the bigger y values, and that's the one that goes first. When we're rotating around the y-axis, we're taking just a given cross-section here and saying which one has the greater x values. Well, that's the square root of y function, so that's the one that's going to go first when we're integrating for a y-axis rotation. So this is going to be pi times the square root of y squared minus, not y, excuse me, minus y squared dy. So let's clean this up a little bit. Excuse me, let's label it. This is the volume. So this is pi integral 0 to 1 of y minus y squared dy, which is pi times y squared over 2 minus y cubed over 3 from 0 to 1. And now let's put some numbers in. This is pi 1 squared over 2 minus 1 cubed over 3 minus, and you see this is one that comes out nice. It's 0 minus 0 in there. So what are these numbers? It's 1/2 minus 1/3, right? We do a common denominator. That's going to be 3/6 minus 2/6, which is 1/6. So this is just pi over 6, right? And that's my answer, pi over 6 cubic units. Not a whole lot. Right? That's a little bit more than a half, right? But that's a pretty thin slice that we have right there. So yeah, I'm comfortable with that being a fairly small number. Okay, so where are we going next? Well, we're not quite done looking at methods for finding solids of revolution. In the next section, we're going to look at some situations where I don't say the disk and washer methods don't work, but where doing them can be a bit of a complicated mess. Right? And there's an alternative method to handling those sorts of things. It's called the method of cylindrical shells. And that's going to be our topic in the next lecture.